Hello, hello, and welcome to my channel on classical physics. Today we will be talking about a problem in circular motion. So here we have a hemispherical ball which has a radius capital R. A small pebble of mass small m is kept at a point in the hemisphere such that the radius from the center of the hemisphere to that point makes an angle theta with the vertical as shown here. So this is the object, this is the angle it subtends at the vertical at the center. There is a coefficient of friction mu between the two surfaces, that of the ball and the object, and a frequency, angular frequency omega is imparted to the ball. We have to calculate the minimum frequency omega for which the block does not slide down the ball surface. So let's get to the task. Now if I create a free body diagram of the small pebble here in this figure, we can see that there is a weight mg which acts downwards at this ball here, mg. Now as the ball would like to slide downwards, there will be a frictional force which will try to oppose the relative motion. So a friction, let's call it small f, sets up which acts in the slanted upward direction to prevent any relative motion to happen. That force of friction, let's call it F. So if we will see here, this will be the angle which the force of friction will make with the horizontal. It will be theta again. If you see here, this angle here is theta, which means this angle is also theta here, and this angle is nothing but what is shown here. So in this free body diagram, this is the vertical, this is the angle theta which it makes with the normal reaction force which the block experiences towards the center of the hemisphere. So in the block, the normal reaction force between the block and the surface acts towards the center of the hemisphere here, making an angle theta with the vertical axis. So accordingly this angle would also be theta, you can see, and as the block rotates with the hemisphere, there will be a centripetal acceleration, and hence if we look at from the non-inertial frame, there will be a centrifugal force we will need to add in the free body diagram, that we call it by m omega square r, where r is the small radius in which this small block makes its own circles. Please remember that the large radius r, capital R, is the radius of the hemispherical ball, but when the ball moves, when the ball rotates, the small pebble here rotates in a smaller circle inside the hemisphere. So that radius is denoted by small r, which is going to be given by a relationship which says r equal to capital R sine theta. You can see it from this diagram. You can see it from this diagram. This length from the center to the pebble is capital R radius. The angle here is theta. So if you draw a perpendicular here, that will be the small radius of this pebble here. So this is a right triangle with hypotenuse is capital R, angle as theta. So the length of the perpendicular would be r sine theta, which is nothing but the radius of the circle on which the small pebble makes its own revolutions. So we have a free body diagram where we have a normal reaction acting on the pebble towards the center of the hemisphere. There is a weight which acts, there is a frictional force which tries to oppose the relative motion acting on a tangential direction, and there is the net centrifugal force. The friction would be given by mu times n normal reaction. And now if we try to balance, now the body is in the forces balance, these forces balance in this object. So if we try to create two equations where these forces balance, we will come up with the weight which acts downwards is equal to n cos theta, which is the vertical component of this normal reaction here. So there are 1, 2, 3, 4 forces. Mg acts downwards, so mg is equal to n cos theta plus friction's component in the vertical direction, which is f sin theta. So n cos theta plus f sin theta tries to balance the weight acting downwards. This is the first equation, from which we come to the second equation, which is in the x-axis. We can see here that n sin theta, which is the horizontal component of the normal reaction, n sin theta, which acts like this here, this is nothing but n sin theta. So n sin theta here is going to be equal to f cos theta, which is the horizontal component of the friction force, f cos theta here, plus m omega square r, which is the centrifugal force. So these are the two equations we get. The first one is mg is equal to n cos theta plus f sin theta. The second one is n sin theta is equal to f cos theta plus m omega square r. Making use of these equations, we can come up here with the value for omega. If you will see here closely, the value for omega is given here: g sin theta minus mu cos theta upon small r cos theta plus mu sin theta. Now you can replace the r with capital R sin theta here, and you can get the expression for the angular velocity omega with which the hemisphere should rotate so that the block does not slide down. So we have used a few physics concepts here. One of them is to try to understand the force of friction, normal reaction, centrifugal force, and the weight which act on this body, and we balance all these forces for a particular omega, and we try to calculate that omega. So this is the minimum value of angular velocity for which the block will be stable. Now, as we keep on increasing this angular velocity over a period of time, a situation would come wherein the block will start to develop a tendency to move upwards. Remember, this time round we had assumed that the block tries to move downwards, and hence the frictional force acts upwards. But as we keep on increasing omega for this hemisphere, this m omega square r keeps on increasing, and hence there will reach a point where the block will develop a tendency to move upwards. So the relative motion it will start to exhibit will tend to happen upwards along this tangent. So at that point, the direction of frictional force would reverse. The friction which is acting upwards till now will start to act downwards, as shown in this free body diagram here. All the other forces remain the same, the weight remains the same, the centrifugal force remains the same, the normal reaction remains the same, but the friction starts to act downwards. There will be another two equations which we can derive from this, and the value of omega we will get for this will be the upper value of omega for which the block will remain steady. If you increase omega beyond that point, then the block will start moving upwards. So I would request the students to come up with that value of omega by themselves, and if there are any doubts, any questions, please feel free to post any comments here, and please like the video. There will be more questions to follow over a short period of time. All the best for your studies. Thank you.